In this video, we solve problem 3.5.3 from Nagle's Fundamentals of Differential Equations, 7th edition. The problem statement says, the pathway for a binary electrical signal between gates in an integrated circuit can be modeled as an RC circuit, as shown in the figure. R stands for resistor, C stands for capacitor. The voltage source models the transmitting gate, and the capacitor models the receiving gate. Suppose the resistance is 100 ohms, and the capacitance is 10 to the negative 10 farads, or 100 picofarads, which can be abbreviated PF. If the capacitor is initially uncharged and the transmitting gate changes instantaneously from 0 to 5 volts, how long will it take for the voltage at the receiving gate, to reach 4 volts? Okay, so they're saying that this pathway for a binary electrical signal is modeled by an RC circuit. Now, in order to answer this question, we need to familiarize ourselves with a little bit of physics in order to set up the appropriate differential equation, solve that differential equation, and then use our solution to the differential equation to answer their question. So this is really a little bit of physics 2 knowledge I'm going to just share with you right now at the beginning of this video. But if you want more information, if you want to really understand what a capacitor is and what an inductor is, you should pick up an elementary physics book or an engineering physics textbook if you go to TCC. All of this information is in there, and they go into the physics a lot more. I'm going to tell you just enough about Kirchoff's laws in order to set up that differential equation and then solve the problem that they're asking us to solve. So here's the background that we need. First, we need to know about Kirchoff's laws. These are physical principles that govern electrical circuits. And here they are. The first law is the current law. It says the algebraic sum of the currents flowing into any junction point must be 0. And then the voltage law is the one that we tend to use. It says the algebraic sum of the instantaneous changes in potential, that's voltage drops, around any closed loop, must be 0. So we're going to add up all the voltage drops, and those should be equal to the voltage being applied to the circuit. Now, this is the part where it helps to have some physics background, but I'm still going to just go over what the voltage drop for each element in a circuit will be. If we're going to use this law, which says that the sum of the instantaneous changes in potential, or the sum of the voltage drops around any closed loop must be 0. We need to know what the voltage drop is across a resistor, across an inductor, and across a capacitor. For RL circuits, those are circuits that have a resistor and an inductor in them, and for RC circuits, like the one in our problem. And those are circuits that have a resistor and a capacitor. So the first voltage drop is the voltage drop across a resistor. Ohm's law says that V equals IR. So the voltage drop across the resistor is proportional to the current passing through the resistor, and that constant of proportionality is a characteristic of the resistor, and we're calling that R. That's the resistance of the resistor. So the voltage drop across a resistor is given by V equals IR. Or often, instead of using this V, we will use an E, or an E sub V. This is the voltage drop, and I think that should be an R there, across a resistor is equal to the current times the resistance of that resistor, and that's a constant of proportionality. Now, if we have an inductor in our circuit, well, it turns out that the voltage drop across an inductor is proportional to the instantaneous rate of change of the current. So that's di dt. And the voltage drop across a capacitor is proportional to the electric charge in the capacitor. Now, the constant of proportionality for the inductor is this given by this capital L, and that is called the inductance of the inductor. The voltage drop across a capacitor is proportional to electric charge Q of the capacitor, and it's equal to this constant times Q. We're using 1 over C rather than C just because of convention. That constant C in the denominator is called the capacitance of the capacitor. Now, any voltage source, like a battery, for example, is assumed to add voltage or potential energy to the circuit. So when I'm looking at a circuit look like this, I'm thinking of this E as my source, my voltage source. And due to Kirchoff's voltage law, this source is going to equal the voltage drop across the resistor plus the voltage drop across the capacitor. And that's going to be enough for us to write down our differential equation. The voltage drop across the resistor is given by I times R, where I is the current. And the voltage drop across the capacitor is this Q times 1 over C. Now, one other thing that you should know is that if Q is the charge on the capacitor, current is the instantaneous rate of change of that charge with respect to time. So if we're looking at how the charge changes on the capacitor with respect to time, if we take its derivative with respect to time, that's giving us current. So that's another fact that you need to know. So current, which is represented by I, is dq dt. This is instantaneous rate of change of charge and we're thinking of this as charge on the capacitor with respect to time. Now for right now, you're just going to have to take my word for it. If you don't want to do any additional research on circuits and how they work and elements of circuits, but if you're curious and if you're saying like, what do you mean charge on the capacitor? If you're wondering like, what all of these expressions really represent physically, you might get a physics book out and check it out. So we've got the voltage source is equal to the sum of the voltage drops. So we're going to have the voltage drop across the resistor plus the voltage drop across the capacitor. And the voltage drop across the resistor is I times the resistance of the resistor. And the voltage drop across the capacitor is 1 over C times Q, where Q is the charge on the capacitor. And I is actually equal to dq dt. So now we have a differential equation involving this function Q that's charge on the capacitor as a function of time. Now the resistance is a constant and the capacitance is a constant, and they actually gave those to us in the problem statement. They told us that the resistance is 100 ohms and the capacitance for a capacitor is 10 to the negative 10 farads. We're assuming the capacitor is initially uncharged, so that means at time t equals 0, Q is equal to 0. So we have an initial condition there. And it says the transmitting gate changes instantaneously from 0 volts to 5 volts. Okay, now let's look at what they said up here. The pathway for a binary electrical signal between gates in an integrated circuit can be modeled as an RC circuit as shown in the figure. The voltage source acts or models the transmitting gate. So it's saying the transmitting gate changes instantaneously from 0 to 5 volts. So at time t equals 0, immediately we've got a voltage source of 5 volts. So we're thinking of E is equal to 5. And then they're asking us how long will it take for the voltage in the receiving gate to reach 4 volts? And we'll get to that in a little bit. but we know that E of t is equal to 5. We know what R is, we know what C is. We can just substitute those into the differential equation and then solve for Q of t. I'm just going to write it a little bit differently. Instead of having the left-hand side equals the right-hand side, I'll have the right-hand side equals the left-hand side. Just switch sides, which is totally fine. And the resistance was 100. The capacitance was 10 to the negative 10. And if you use the units of farads and ohms, all of this will be, the dimensions will be correct for this. And then we'll have 5 over here. And then, of course, 1 divided by 10 to the negative 10 is 10 to the positive 10. You can bring that up to the numerator. And then if you want to, you could divide everything by 100, or similarly, dividing by 10 squared. And you'll have dq dt plus 10 to the 8th times q equals 5 times 10 to the negative 2. Okay, now you have a couple of options for how to solve this. You can use an integrating factor if you want to, but there's no function of t over here. I would just separate the variables. I think that would be easier. So we can subtract this from both sides. And then multiply both sides by dt and divide both sides by this function of q. And that actually should be in the parentheses there as well. Sorry about that. And what we get is this. We have 1 over 5 times 10 to the negative 2, or 0.05, minus 10 to the 8th times q, times dq equals dt. And then you can anti-differentiate on both sides. On this side, I would use a u substitution to anti-differentiate. We have this. Then du will just be negative 10 to the 8th times dq. So negative 1 over 10 to the 8th times du is equal to dq. So we'll have 1 over u, and dq is du times this expression, which we could just write as negative 10 raised to the negative 8th power. And of course, the antiderivative of that is just natural log of the absolute value of q, or excuse me, absolute value of u, which is this expression when you back substitute. Okay, and of course the antiderivative of 1 with respect to t is just t plus a constant. And if you want to get rid of this negative 10 to the negative 8th, you could just multiply both sides by a negative 10 to the positive 8th. Oops. And c times that will just give me a different c. And then to get rid of the log, I'll exponentiate. E to the c1 is just a different constant. And you can split this up into 2 pieces. E to the a plus b is e to the a times e to the b because of our exponent properties. The bases are the same, so you add the exponents. We can do that backwards as well. So I'll have e to the c1 is c2 times e to that power. And we're trying to get q by itself, so we can subtract the 0.05 from both sides. And then divide both sides by negative 10 to the 8th. And I'll just call this new constant C3. And this was negative 5 times 10 to the negative 2. And we're dividing that by a negative 10 to the 8th. So if you want, you could say a negative divided by a negative is a positive, and then that would make that a 5 times 10 to the negative 10 right there. So that's our charge as a function of time on the capacitor. Our charge on the capacitor as a function of time. Now, if I want to use this, I need to find the value of that C3, that constant. And I can find the value of that constant C3 using our initial condition. We were told that the capacitance is this if the capacitor is initially uncharged. And then we're asked this question. So they're telling us that the capacitor is initially uncharged, which tells us that at time t equals 0, the charge on the capacitor, that's Q, is equal to 0. So we can use the fact that when t equals 0, Q equals 0 to find the value of C sub 3 in this equation. So let's use that now. So if we substitute in t equals 0, here we get that. That's just C sub 3 plus this. And then if we set that equal to 0 and solve for C sub 3, we see that C sub 3 must be the opposite of that. So negative 5 times 10 to the negative 10. So our Q of t, this is charge on the capacitor as a function of time, is negative 5 times 10 to the negative 10 times e to the negative 10 to the 8th times t plus 5 times 10 to the negative 10.